everyone. In this video we're going to cover the second part of PN junctions at open circuit, which is section 3.4 of your book. On the first video we already covered how diffusion current is generated and what's the depletion region. So now we're going to look into drift current. So we have this picture right here. We know that we have a positive charge on the N side, a negative charge on the P side, and that an electric field is created from right to left. So we have this electric field. So now we're going to talk about the minority carriers, because on diffusion current, if you remember, it was due to majority carriers. So now we're going to look about what happens to the minority carriers. Remember, these minority carriers are thermally generated. So let's see, on the N side, the minority carriers are holes, right? So you have, let me see. So you have holes right here, or let me just draw them in red. I think that's better. So you have holes. These are minority carrier holes that are on the N side, and these holes that are near to the depletion region face this electric field, and we know that holes go in the direction of the electric field. So there is a current going from the N to the P side due to the holes in this direction. So we have that current over there. Now let's see what happened to the minority carriers on the N side. So the minority carriers on the N side are electrons. So you have electrons right here. These thermally generated minority carriers that are near to the depletion region, they get attracted to the positive side, or we know that electrons flow in the opposite direction as the electric field. So we have electrons going from here to here, and that creates a drift current due to electrons on the opposite direction, because remember, as we've been saying, current by convention goes in the opposite direction as the electron flow. So there is a drift current going from right to left, that due to electrons. So the overall current that I'm going to draw here, and drift current is IS and goes from right to left. So now if you can notice, we have diffusion current going from left to right, and an opposing drift current going from right to left. So in equilibrium, because this is an open circuit, there is no other place where the current can flow. So in equilibrium, we have that our diffusion current has to be equal to the drift current. And something else that happens in equilibrium is that, you know, the charge here on the right side, a positive charge, that's Q plus, should be equal to the charge on the N side. That always happens in equilibrium. Another thing that we have to notice here is that the width of each side of the depletion region, I try to draw them as equally as possible. We're going to do it, these are the length of the depletion region in each side. Obviously this one is N. And I try to draw them equally, because in this case, which is not a realistic case, but it was good for explanation, the concentration of donors is equal to the concentration of acceptors. So that was just one node, and let's come back to the charge. So we have that the charge on one side is always equal to the charge on the other side, because we are on equilibrium. So let's look at the equations from charge. So we have that the charge, the positive charge right here, is proportional to the electron charge. This is cross-sectional area, this is the width, and obviously the concentration of donors. Why donors? Because remember from here that our phosphorus, which is a donor, had a positive charge. And a similar thing happens with the negative charge. You have electrons, cross-sectional area, the width of the p side, and the acceptor concentration. So that's the formula for charge, and remember they're equal. But let's see what happens. So the previous case was that the concentration of donors was equal to the concentration of acceptors, but what happens to that width if we make a more realistic case where the number of acceptors or the doping concentration of acceptors is greater than the doping concentration of donors? So in that case, let's see, we're going to keep focusing on these formulas. So if you're increasing the number of acceptors, but you're keeping the charge equal, so this charge is not going to change, but you're increasing this concentration of acceptors, what's going to happen is that you're going to decrease the width of the depletion region on the p side. And a similar thing is going to happen here. We're going to keep these two equal, these two charges. So if you're decreasing the concentration of donors, you are going to be increasing the width on the n side of the depletion region to keep things at equilibrium or to keep things equal. So that's what we're going to see here on the width of the depletion region. So if the concentration is greater on the acceptor side than on the donor side, what you're going to see is that the width on the p side, let's see if I can do this, is going to be reduced, and the width on the n side is going to be increased. So keep it that way. So you're going to have more bound charges here than you have on the other side. So what's important here is that if the concentration of acceptors is bigger than the concentration of donors, the depletion region will extend into the area with less concentration. So Xn is going to be greater than Xp. And you guys can see that here. So we have this being Xp and this being Xn. So again, the width on the lightly doped side is wider than on the other side, on the highly doped side. Let's see what else. So just to end with this, we're going to look at this more realistic case where Na is greater than Nd. So we're going to have equations for width. This is the width, and that's the total width of the depletion region. So we're adding the n side and the p side, and that is equal to the square root of 2 times this guy right here is a constant, that's permittivity. I think that has double T here, permittivity of silicon. And that permittivity of silicon is equal to 11, sorry about that, 11.7 times the permittivity of free space. And then it's also proportional to, or inversely proportional to, the concentration of atoms or of sectors and the concentration of donors, and is directly proportional to the square root of the built-in voltage. And from that equation you can find Xn and the width on the p side as well. And just lastly, the charge. So this is the junction charge, which we said is in equilibrium, so it's equal to the charge on the plus side and it's equal to the charge on the minus charge, the magnitudes. And that can be found by this equation, which is cross-sectional area, charge, permittivity of free space again, this parallel combination of the concentration of donors and acceptors, and the built-in voltage. So those are the formulas that you will need. And in this video, we already talked about drift current, the width of the depletion region. We talked about depletion region and diffusion current on the previous one. So we can go ahead and look at these review questions. In these review questions, we have what current is due to the majority carriers. So it's very important that you guys know that the diffusion current is due to majority carriers. Then what current is due to minority carriers? You guys should know that that's the drift current. And what happens if ND, the concentration of donors, is bigger than the concentration of acceptors? What side of the depletion region is wider? So the lightly doped side is the one that's going to be wider. So in this case, it's going to be wider. XP is going to be greater than XN. So that's the opposite of what we looked at. And that's it for now. And on the next video, we're going to cover what happens when you apply a voltage to a PN junction.